while we collect the last few people outside. As I said, we're going to have 2 tutorials. This is the first one, which will be given by Timo Spindeler. I'll just say very briefly, because during the meeting we won't introduce everyone in so much detail, but we still do have a few people here outside of the meeting. So I will say that he's the youngest of our speakers today. He finished his PhD in 2018 with Michael Backe in Bielefeld. He then spent a postdoc at the University of Alberta in Edmonton, working with Nicola Strungaro, who unfortunately will not be attending the meeting. And since 2021, he's back at Bielefeld as a postdoc. And recently, together with Daniel Lenz and Nicola Strungaro, they've done really important work in making the connection between the structures that we're interested in and the diffraction diagrams that they produce. Daniel Lenz will give an invited talk describing this connection, but for the few of us who don't work every day with almost periodic functions and almost periodic measures and point sets, this introduction will hopefully give us the background that we need in order to understand this really important, I think, result that they've derived recently. Timo, please.
Yeah, thank you very much for the introduction and the opportunity to speak here. And I wanted to explain at the beginning why these functions are interesting, but Ron just teased it. So we'll learn about this on Wednesday, how they are connected to the diffraction spectrum. Okay, good. And in order to do so, I'd like to tell you about almost periodic functions. So let's start with a classical notion with periodicity. We all know, you all know about it, but let me just briefly recall it. A function, real or complex valued, is called periodic. If there's a number such, if I shift the function by this number, then it looks exactly the same. So in mathematical terms, f plus x plus l is the same as f of x. And of course, you all know classical examples like the sine, the cosine, the complex exponential function. And one of the interesting properties that these functions have, they can be, at least when they are nice, and I'll explain in a second what nice means, these periodic functions can be expressed as a Fourier series. Yeah? So we can take a function f and write them as a series with coefficients cm and exponential terms where L is still the period. And even better, we can compute those numbers, those coefficients. And how do I get them? Well, I just integrate over the period from 0 to L, the exponential function, e to the minus 2 pi I m divided by L times x, f of x dx, and divide by L. And if I do this, then I can write the function as a Fourier series. Now, we need to be a bit careful here. Why? Well, what we have here is a series, an infinite, possibly infinite series. And whenever we deal with series, we need to ask ourselves, does it converge? Because not all series converge. So, but in many cases, so for example, if the function f is continuous and has bounded variation, which just means that the function doesn't oscillate too heavily. So the classic counterexample is x times sine 1 divided by x. Yeah? If x approaches 0, it starts heavily oscillating, and it gets worse and worse the closer it gets to 0. This would not be of bounded variation. But as long as it is continuous and doesn't oscillate too heavily, then it actually, the series converges pointwise everywhere to the original function f, which means exactly this. Yeah, I take the partial sum, take the limit of the series, and for every x, it converges to f of x. Okay, but even if we are not in this nice situation, we still get a different, in many cases, a different kind of, a different kind of convergence. If, for example, f is in L log 2, which just means I take an interval, I take this modular square of the function, and then it is integrable. Yeah, the function is integrable, this modular square of the function is integrable over every compact interval. So, for example, bounded functions. Yeah? And in that case, I always know that it converges in the so-called 2 norm. What does it mean? Well, it means exactly what we have here. I take the partial sum of the Fourier series, divide by, subtract the function f, take the modulus squared, integrate from 0 to L, take the limit n to infinity, and then it goes to 0. So we do have convergence, but just in a different way. Yeah, but in many situations, we're in the good case here, that the function f is continuous and bounded, then we don't need to worry about it. Then we get exactly what we hope we would get, that the Fourier series converges pointwise to the function f. But that, just as a side note, that we sometimes have to be careful. Now, as Mark already pointed out in his talk, not everything is perfectly periodic. That's a shame, but that's the hard truth. And even worse, it would be nice if we just take 2 periodic functions and the sum would be periodic again. Yeah. Again, this is not true. But these functions are also very interesting, right? So, yeah, can we maybe somehow characterize those functions which are, yeah, not periodic, but close to being periodic? So, at first, let us look at an example here. So, what do we have here? We have the function f, which is the sum of 2 periodic functions. Yeah? F of x is cosine of 2 pi x plus cosine of 2 pi square root of x. And an easy way to see that this is not periodic is if you consider the value x equals 0, then f takes the value 2. Yeah? F of 0 is 2. But no other point. Yeah, for no other x, I get f of this x is equal to 0. So it can't be periodic. Okay. But what happens if I shift the function by, well, let's say 5, yeah? Then we see in the first line that if I take the function f and draw a slope around this function, then f of x minus x plus 5, it is still in the slope. Yeah, it's not perfectly the same as f, but at every x, it is very close. It is always inside the slope. And we can do even better. If we not consider f of x plus 5, but f of x plus 12, this is the second line, then we can make the slope even smaller. And if we take n equals 29, so f of x plus 29, we can make the slope even thinner. Okay. So this suggests that there might be a notion of periodicity where I take the function f, the function f plus some other number, compare them, and I see, oh, they're pretty close. Not perfectly the same, which in the case of a periodic function, but as we see, we can get pretty close. Now, and this generalization, this has been studied by Bohr, not Niels Bohr, who you are probably all familiar with, but his brother, Harald Bohr, and he came up with the following definition. Yeah, he said, okay, let's take a real or complex continuous function f, and it is called Bohr almost periodic if, yeah, first I'll state the definition, then I'll explain what happens. So if for every positive epsilon, the set p epsilon, which is the set of all t, such that f and the shifted function f of x plus t in the supremum norm is less than epsilon, that this set is relatively dense in R, which means that there's an interval I such that R is I plus PE. Okay, now let me explain what it actually means. So we have seen that if we shift the function by the right numbers, then it looks roughly the same. And this roughly the same is this. I take the function f, subtract f of the shifted value and the supremum, so the maximum distance of those two should be small. Yeah? And this should be true for not just one value, t, but for a relatively dense set. So what does relatively dense mean? Yeah, I need to find an interval such that R can be written as I plus PE. So for example, let me just give an easy example of a relatively dense set. The integers. Why? I can write every real number as an interval 0, 1, plus an integer, right? For example, 3.5 I can write as 3, which is an integer, plus 0.5, which is in the interval 0, 1, yeah? Or I can write pi as 3 plus, which is an integer, plus 0.141, and so on, which is in 0, 1, okay? So this is what relatively dense means, which in particular means that if I take different values of t, the one closest to each other can't be too far away. This is what it basically means. Okay. Now, do these Bohr almost periodic functions have some nice properties? Well, we just saw that they can be described using these so-called epsilon periods, but they have other properties. For example, they can be written as a uniform limit of a sequence of trigonometric polynomials. Yeah? So, what is a trigonometric polynomial? Oops, sorry. Well, such an expression. I have a series with exponential terms and coefficients. Yep. Yeah, and the third property I don't really want to spend. It's mathematically nice to have it, but what we need here is the epsilon almost periods and being able to approximate them uniformly with trigonometric polynomials. Now, it would be nice if we could do something similar with those, what we did for the periodic functions, with the Bohr almost periodic functions. So maybe if I have a Bohr almost periodic function, can I again write them as some kind of Fourier series? Well, we can't do it exactly the same way. Why? Because if we go back, what we did here, to compute the coefficients, we integrated over the length of the period. Yeah, but we don't have periods anymore. So if we want to do it, we have to do it a bit differently, but it actually works. So how does it work? Okay, let's assume we have a Bohr almost periodic function. And now for a real number k. One question? Yeah. So what can we do instead of integrating over the period? Well, we integrate over the interval minus LL, and the integrand is the same. It's e to the 2 minus 2 pi I kx f of x dx, and divide by 2L, and let L get bigger and bigger. And one can show that this for a Bohr almost periodic function always exists. It's fine. And one can also show that the set of k for which this is non-zero is countable. And knowing this, we can write down the so far formal Fourier-Bohr series attached to the function f, which looks very similar to the Fourier series for periodic functions, such that, but we have to compute the coefficients a bit differently. Yeah, and again, technically we have to think about convergence and so on, and if it converges, is the limit truly f? And yeah, but one can see if it converges uniformly, this expression, then the limit is indeed f, the function we started with. So yeah, also for those Bohr almost periodic functions, we can have Fourier-Bohr series. Okay, and there are some interesting subsets of the Bohr almost periodic functions, and some of them can be characterized by the set I, the set of those AK which do not vanish. So, for example, can I maybe characterize periodic functions this way? Yeah, we can. So let's assume we have a Bohr almost periodic function, then it is periodic with period L, if and only if the set I is a subset of 2 pi divided by L times the integers. Yeah, and well, if we are not exactly in this case, but close, so if the set I is a subset of 2 pi L times Q, so we allow rational numbers here, then such functions are called limit periodic. And yes, many people of you will think, wait, limit periodic, isn't that defined differently? Well, it is actually equivalent. So it is equivalent in saying this is a uniform limit of a sequence of periodic functions. Both is the same. Okay, we do have more. For example, one notion we already heard in the last talk, quasi-periodicity. And one way to describe it is also with the set I. So, by the way, I'll give a couple of examples soon so we can see the difference better. Yeah, but let me just go through the list and then we'll have some examples. Now, F is called quasi-periodic if the set I contains at most finitely many fundamental frequencies. And what do I mean by this? By that I mean there are finitely many elements, let's just call them mu1 to mu_m, such that every other element in I can be written as a linear combination of these mu_j's with integer coefficients. Like I said, example in a couple of seconds. And last notion for the moment, limit quasiperiodic. That is easy again. A function is called limit quasiperiodic if it is the uniform limit of a sequence of quasiperiodic functions. Now, okay, this is a bit dry right now, so let's give it a bit life. Let's consider examples. Yeah, one little diagram before that, which is not difficult to see. If a function is periodic, it is obviously limit periodic. Just consider the constant sequence of this function. It is also quasi-periodic. Yeah, if I is in 2 pi, if I is in 2 pi divided by Lz, it is obviously in 2 pi divided by Lq because the integers are a subset of the rationals. And if it is limit periodic, it is limit quasi-periodic because every periodic function is quasi-periodic, and every quasi-periodic function is limit quasi-periodic for the same reason every periodic function is limit periodic. And there's no connection between limit periodic and quasi-periodic functions. Now, I hope now, yeah, here we come to the examples. Let's go to the function I already showed you, the function f of x equals cosine of 2 pi x plus cosine of 2 pi square root of x. I already told you it is not periodic, and I explained why. It is quasi-periodic. Why? Well, this function, well, we can easily write it as Fourier series because cosine, we know we can write as 1 divided by I, e to the ix plus e to the minus ix. So we have already our Fourier expansion. And what is I? Well, I is in that case plus and minus 1 and plus and minus square root of 2. So it's 4 elements. Yeah, and if I have only finitely many, then obviously I can write every element as a finite combination of those 4. Yeah, and it is not limit periodic. This requires a tiny little computation, but it's not difficult. We can use this characterization. imagine there is such a number L, and then try to describe the 1 minus 1 square root of 2 minus square root of 2 using this characterization, writing them as 2 pi divided by L times the rational number, and you'll see 1 and square root of 2, they cause issues. That doesn't work. So yeah, this is an example of a quasi-periodic function which is not periodic and not limit periodic. Okay, next one. Let's consider this function. F of x is the series over all n at least 1 divided by n squared, sine of 2 pi 1 divided by 2 to the n x, and one can see this, this is limit periodic, but neither periodic nor quasi-periodic. Well, limit periodic, this function is periodic, the sum of those is periodic, and then since it's a series, it's a limit of those partial sums, so a limit of periodic functions, and therefore it's limit periodic. Yeah, one can show, similar to the example above, that it's not periodic, because, well, yeah, again here we can see what the set I is. It's plus minus 1/2, plus minus 1/4, plus minus 1/8, and so on. And yeah, we cannot describe this. I mean, this is not a subset of 2 pi divided by some L times the integers. And why is it not quasi-periodic? Well, I just told you I is plus minus 1/2, plus minus 1/4, and so on. And if we would now try to pick a finite number of those, yeah, for example, 1 to the 2, 1 divided by 2 to the n1 to the 1 divided by 2 to the 2nk, and would then choose an arbitrary 1 to the 2 pi, 1 to the 1 divided by 2 to the n, then we can see I can't use those finitely many. I can't find a linear combination with integer coefficients of those finitely many to get the value 1 divided by 2 to the n for a specific n. It doesn't work in all cases. So limit periodic, but not periodic and not quasi-periodic. Oops, sorry. And one last for this slide. One is missing. This one. F of x is sum over all n at least 1 divided by n cube, sum m from 0 to n, sine of 2 pi m divided by 2 to the n x. And this is limit quasi-periodic, because for finite n, this here is a quasi-periodic function, because we again have minus 1/2 plus 1/2, minus 1/4 plus 1/4, but only finitely many, so it is quasi-periodic. So also the sum, but the limit, and if you consider the limit, it's limit quasi-periodic, but it is not quasi-periodic because I can't just use finitely many of those 2 to the n. I need infinitely many, and it's not limit periodic. Again, one can try to prove it so one can try to use this characterization and then see you run into issues, you run into contradiction. Okay, so I hope those couple of examples will show you a bit of the difference between those couple of notions. And let us consider one famous guy we all know, Fibonacci. And I mean, yeah, Mark already described how you can build the Fibonacci chain, so I think I can skip this part. And what we do now, we have the Fibonacci chain with our tiles, and on every tile we put a triangle of height 1. And this is our function, this triangle once. And we all know if we have a Fibonacci chain and we consider the diffraction, it's pure point. But the function f itself, this one, is not Bohr almost periodic. Why? Yeah, that would mean I can find a number, shift the function, and then the difference would be as small as I want. Okay, if I try to shift the function, the first few would have to be exactly the same, right? Because if it's just off by an amount, I'm already lost. But it doesn't matter by which value I shift. At some point, I find a smaller triangle. I mean, they all have had one, but the length is different. A smaller and a larger one. And by the shifted version, the larger and the smaller one are in the different order. Yeah, but then you can immediately see those differ too much. I can't make this smaller as an arbitrary epsilon. So here we do have a function which is not Bohr almost periodic, but still gives rise to a pure diffractive object. So if we want to describe or characterize those structures which give rise to pure point diffraction, Bohr almost periodicity is too strong. I mean, yeah, every Bohr almost periodic structure will give you a pure point diffraction, but the other direction is not correct. So we have to think about something different. And what we do now, I mean, I told you now a bit about Bohr almost periodic function, about some subsets, periodic, quasi-periodic, and so on. But now we need to look at a bigger class, because as I just told you, those are too restrictive. Okay. So, yeah, how could we choose a bigger class? Well, for this, we can look maybe not at the supremum norm, which we used for the Bohr almost periodic functions, but we can define this mean. So what do? I take the function f, I integrate over a symmetric interval, minus n to n, divide by 2n, and take the limit. Well, lim sub, because for some functions the limit might not exist, but the lim sub does if we take the absolute value. And this is our new semi-norm. We don't take the supremum norm, but this semi-norm. And then we use exactly the same definition as for Bohr almost periodic functions, but here we don't choose the supremum norm, but this one. Otherwise, it's exactly the same. And since the supremum norm is stronger, this means every Bohr almost periodic function will satisfy this, but not the other way around. Okay, but why are they so special? I mean, I could just write any semi-norm. Why exactly this one? Well, to be fair, this we'll see on Wednesday why. This is just a preparation. But it turns out this is exactly the kind of almost periodicity we need for pure point diffractiveness. Okay. So do we have any examples for mean almost periodic functions? Well, I just said Bohr almost periodic functions are all mean almost periodic, which in particular means every periodic, every limit periodic, every quasi-periodic, and every limit quasi-periodic function is mean almost periodic. And one can show this function I showed you earlier, this triangle function on the Fibonacci chain. This is mean almost periodic. This is an example. Okay. I'll be very brief here. I don't want to spend a lot of time on measures, but for what we will learn on Wednesday, it is good to just get a very rough idea about what a measure is. For those who know distributions, it has a similar taste. What it does, it takes a continuous function of compact support and turns it into a number. Yeah, that's what a measure does. And yeah, this is just a technical property. It's continuity in a certain topology. Don't want to spend too much time on this. Just, like I said, think of it as something that takes a continuous function of compact support and turns it into a number. So, one easy example. If t is just a real number, then we can take this delta t. What does it do? It takes the function phi and evaluates it at t. Now you can say, wait, this is just the Dirac distribution that I know. Yeah. The only difference is that I use different test functions. So here I take continuous functions with the compact support, and for distributions they would usually be differentiable. Yeah. But for all functions which are continuous compactly supported and differentiable, it actually does the same. This Dirac measure and the Dirac distributions, it does exactly the same. And maybe a second example, if we have a nice function, let's say bounded and continuous, then the following mapping, I take f and map it to the integral f of x phi of x dx, which is a number, yeah, it's an integral. This is also a measure. Yeah, but like I said, I want to keep this brief. This is as much as I want to tell you about measures, except one thing. Because now, what we want to do is transfer the property of mean almost periodicity from functions to measures. And this we can do by convolution. I mean, you all know the convolution between functions. And the convolution between a function and a measure is pretty similar. So let's take an integrable function and a measure. And how do we define now the convolution, m convolve with f? Well, it is just that I don't take the function f, but its shifted version, x minus dot. This is the function I evaluate. Or in other terms, if I write it down as an integral, it's the integral over r, f of x minus t, d mu of t. So why do I need this? Because now I'm able to do exactly what I said, carry over the concept of mean almost periodicity from a function to a measure, because now we call a measure mean almost periodic if mu convolved with psi is a mean almost periodic function, if this is true for all psi, for all continuous and compactly supported function. Yeah? So if I want to know if mu is mean almost periodic, I convolve it with every continuous function of compact support. And if this always is a mean almost periodic function, then the measure is mean almost periodic. So examples. Well, we can take a mean almost periodic function and then just consider the following measure. Phi is mapped to integral over r, f of x, which is the mean almost periodic function, phi of x dx. This gives us a mean almost periodic measure. Or another example, we take a point set, lambda, which is exactly the Fibonacci chain. And on every element of the chain, I place a Dirac measure. Yeah, and the resulting measure is, again, a mean almost periodic measure. Yeah, so far so good. Now we have a new version of almost periodicity, but it turns out we need a bit more. We need another notion, and this is called Besicovitch almost periodicity. And what is the idea here? Let me go a couple of slides. Here. So I told you that for Bohr almost periodic functions, it doesn't matter how I characterize them. I can use the epsilon almost periods, or I can write them as a limit, uniform limit of trigonometric polynomials. Now you would think, okay, we took instead of the supremum norm, this seminorm I defined, and for this seminorm, it works exactly the same. Nope, it doesn't, surprisingly, as we will see now. So what do we do here? We define Besicovitch almost periodicity via approximating approximating via trigonometric polynomials, but not uniformly, but using the seminorm I introduced. And if this is true, if I can approximate them with trigonometric polynomials, then I call a function Besicovitch almost periodic. And again, if I have a measure and I convolve with the continuous function of compact support, and it is always a Besicovitch almost periodic function, then we call the measure Besicovitch almost periodic. Now, and this is what I meant. It turns out for this seminorm, approximating by trigonometric polynomials and characterizing via epsilon or almost periods is not the same. For the supremum norm, yes. For this one, no. It turns out that approximating by polynomials is stronger. It's a stronger property. if I can approximate it by trigonometric polynomials, I always have a relatively dense set of epsilon almost periods, but not the other way around. Examples will follow in a moment. Okay. One last notion, which will also be important. I promise, this will be the last notion of almost periodicity. And then I'll give you a couple of examples. Okay. Now, this looks pretty similar to the other semi-norm I defined. The only difference is this guy here. So instead of integrating over the symmetric interval minus n to n, I consider the supremum over all shifts of this interval. Yeah, which is of course a stronger notion. But then I do exactly the same. Again, I ask which functions can I approximate via trigonometric polynomials with this semi-norm. And again, we carry over the same way to measures as usual. Now, like I said, this is stronger because there's a supremum inside, which gives us the following chain. Every Bohr almost periodic function is Weyl almost periodic. What I just called, what I just showed you, the property is called Weyl almost periodicity. Okay, so if we now compare them all, Bohr almost periodicity implies Weyl almost periodicity. Because of the supremum, which makes it stronger, it implies Besicovitch almost periodicity, which in turn implies mean almost periodicity. So we have seen this guy here is too strong to characterize pure point diffraction, and it turns out this one is what we need. And like I said, more on Wednesday. But still, these two will also be important. Also Wednesday. Okay, and now let's get back to examples to show you that none of these arrows can be reversed. None of those notions are actually equivalent. Okay, first one. Yeah, this one I'd like to draw because if you look at it, it's not immediate what happens. So let me just try to explain it. So on the interval -1, 1, it is 1. Then on the interval -2, -1, 1, 2, it is 0. Then -4, -2, 2, 2, 4, it is 1. -8 to -4, and 4 to 8, it is 0 again, and it oscillates. I make the intervals larger and larger, and then it always jumps between 0 and 1, 0 and 1, 0 and 1. Yeah? Now, this is a function one can show is mean almost periodic. What are the epsilon almost periods? These 2 to the k guys. If I shift by the correct 2 to the k, I can show that the function and the shifted function are very close in the semi-norm. Now, how do I see that I cannot approximate it by polynomials? That is not obvious at all, right? The trick is, there's actually a different characterization for Besicovitch almost periodicity. I don't want to go through all of it, but in particular it means that if I take the absolute square of the function, and this is basically the classical mean. Yeah, I take the absolute square, integrate it from -n to n, divide by 2 to the n, then this limit has to exist. And for the function I just showed you, this limit, one can actually compute it, does not exist. So it cannot be Besicovitch mean almost periodic. Okay, so we have an example which is mean, but not Besicovitch. Okay, now, what is an example of a Besicovitch mean almost periodic function, which is not Weyl? Okay, again, let me explain because I can draw here. Now, first, this function looks a bit strange. It's very easy. It's just a triangle. Nothing scary, just a triangle. Now, and what do we do now? We consider the set of square-free integers. What is that? We take the integers, we all know. Yeah, the integer z, and now we throw out points. So we take the union over all primes p squared z. So we take the integers here and start with the first prime, 2. So that means we throw out all multiples of 4. So 4 minus 4, 8 minus 8, 12 minus 12, and so on. Everything that is divided by 4 is thrown out. Then the next prime, 3. Yeah? That means we throw out everything that is divisible by 9. Plus minus 9, plus minus 18, plus minus 27, and so on. And we continue. Next prime is 5. So we throw out every divisible by 25, 5. Then 7, we throw out everything divisible by 49, and so on. And the set of integers that remain after that process is called the set of square-free integers. And if we now put this triangle, this G, over every remaining element, yeah, then this function is Besicovitch, almost periodic, but not Weyl. Why? Let me remind you, what was the difference? The difference was the supremum over all intervals minus n to n, minus n plus 2, n plus 2, this interval. Now, in this set has holes, and if I shift it such that I always are in a hole, I can make it such that I cannot approximate it by, I can approximate it by polynomials in the weaker norm, but not in the stronger because of the shift. I can shift in such a bad way that it's not possible anymore. Okay, and one last example, which is actually pretty easy. You already know it. Weyl, but not Bohr. Of Fibonacci again. The one I showed you, yeah, with the triangles on the tiles. This one can show, is Weyl almost periodic, but not Bohr. Yeah, those are, I hope those helped you again to visualize a bit the differences between those. And yeah, those are the kinds of almost periodicity I wanted you to show, and which will be useful for the talk on Wednesday. And yeah, with those examples, I would like to stop here. And
thank you very much. I'm sure we have a lot of questions. So let me just start. So if I think just of a Dirac comb instead of what we call delta functions on the Fibonacci chain, is that Weyl almost periodic?
it is. Yeah.
And how do I immediately see that? I guess that was.
Well, the proof I know is a bit technical because it goes to dynamical systems. And do we have an easy way to see it?
Follows from the general color-project structure.
Yeah.
Of these regular models, it's the opposite to Weyl almost.
Okay, so I just tend to think that they all lead to pure point diffraction, but here are the differences between what might lead to pure point diffraction. So this is the intuition that many of us miss. The differences between the different classes. Yeah.
Always ask for the real space characterization. Yeah? So the question is, what's the real space characterization of being pure point diffractive? Yeah? And it's not Bohr almost periodic, that's too strong. And it's actually mean almost periodic. But then the nice structures we are working with, like the color-project sets with a nice window, they are all mean almost periodic, and they go all the way up to Weyl, but not to Bohr. So you don't have pointwise convergence. That's the point. Yeah? And let me add this. Whether you want it or not, to understand this thing, you cannot work with finite dimensional vector spaces. Yeah? You are hit by infinite dimensions. And in infinite dimensions, typically, the unit Bohr, with whatever norm you start, is not compact. And that means different norms lead to different convergence concepts. So in math, I don't know, analysis 102 or whatever, you learn that in RD, all norms are equivalent. So it doesn't matter which one you use to talk about convergence. Here you can't do that anymore. So different norms lead to different convergence, and they mean different things. That will Daniel will explain that on Wednesday in his talk. Yeah? So you do have a convergence notion here as well, but it's much weaker and it's more in the spirit of mean convergence. Yeah?
Does anyone want to ask another question? So we're actually ahead of time, right? So we'll break for about 15 minutes and maybe 20 minutes and resume. So let's say 4:35. Good. There might still be coffee out there, I'm not sure, but let's check.